All right, in this review video, we are going to review over probability. So in your table of contents and at the top of your notes, write probability review. We're going to review simple events first, and then we'll move on to compound events. First, with simple events. Remember how to determine the likelihood of a situation. It goes from impossible to certain. Impossible means a 0 probability. Certain means a 100% or 1 possibility. Probability, why am I saying possibility? Probability, hello. As likely as not is 1/2, 0.5, 50%. If it is less than that, we say it's unlikely. If it is greater than that, we say it is likely. So it really can be anything between 0 and 1/2 to be unlikely, anything between 1/2 and 1 to be likely. And we can use probabilities to make predictions about a population. So if we know that the probability of a person no-showing is 0.1 or 10%, the airline expects 1/10 of ticketed passengers not to show up, then we can use that to calculate how many seats would we expect to be full. So if we multiplied the 210 tickets for airline A times 10%, that would tell us that we would expect 21 no-shows. So I would subtract the number of tickets sold minus the number of no-shows. How many seats are going to be full then? 189 seats will be full. Okay, that would leave 11 available if the flight has 200 seats. Whereas with this other flight, they sold 330 tickets. So we'd multiply that times the 10% probability. How many no-shows? 33 no-shows. So then we would just subtract that, 330 minus 33, and that would give us 297 seats are going to be full. And if it has 300 seats, that means only 3 would be available. So this flight would have more empty seats. They would have 11, I think we said? Yeah, 11 versus 3 on the other flight. So we can use probability in that way to make predictions about situations. All right, some terms that you need to know. They should already be in your notes from our probability unit. An action is a process with an uncertain result, like rolling a number cube, spinning a spinner, flipping a coin. These are all actions. An outcome is a possible result of an action. So like heads, tails, even number, something like that. The set of all possible outcomes is the sample space. That's where we list all the possible outcomes. And then an event is a single outcome or a group of outcomes in a sample space. So we would say rolling a number less than 3, that would be an event. Spinning blue, that would be an event. So make sure you know the difference between those terms. All right, finding the relative frequency. This is just like finding the experimental probability. Our little formula here is the number of times the event occurs over the total number of trials. Remember that a trial is each observation of the action. Each time you actually do whatever the experiment is, like each time you flip a coin, each time you spin a spinner, the total number of that would be the total number of trials. So here, what is the relative frequency of spinning a number less than 4? We would add up the frequencies of spinning 1, 2, and 3. So 10, 12, and 4. That would give me what? 26 out of 40. And then depending on how they tell you to write it, they may tell you to write it as a fraction. In that case, we would just simplify and get 13 out of 20. Or they might say that you could write it as a decimal. In that case, it would be 0.65. That would be the relative frequency. You just have to read the directions to know what form they want it in. So that is relative frequency, which is just the same as experimental probability. Remember our probability notation, whatever is in the parentheses is what we're finding the probability of happening. And our little formula is the number of times the event occurs over the total number of trials. And it works just like the relative frequency. So here, what would be the probability of asking for plastic bags? Well, we see from our little table that 18 people requested plastic bags. 18 out of, what is the total here? 18 plus 6 is 24. So that would be 32 total. So 18 out of 32. If I simplified that, that would give me, what, 9/16 as a fraction. As a decimal, I would just divide 9 divided by 16, 0.5625, which would be 56.25%. You would just move the decimal 2 times to the right to convert it to a percent. Okay, so that is experimental probability based on the data from a table. All right, next, theoretical probability is what should or would be expected to happen. And so you're not thinking about what actually did happen when you did the experiment. You're thinking about theoretically how many sides are on a number cube, how many possible sides are there that you could flip on a coin, that kind of thing. And our formula is the probability of the event equals the number of favorable outcomes out of the number of possible outcomes. So let's look at this. Just based on looking at the spinner, we don't have any data of spinning it 100 times or whatever. We're just looking at what is on the spinner. We can find the probability, and this is the theoretical probability. How many sections are red? There are 3 out of 8. So our theoretical probability, 3 out of 8. Red with an odd number, I just see one of those, so 1 out of 8. Green, 2 out of 8, which is 1/4. A number less than 10, that looks like 100% or 1 whole. Yellow would be 0 because we don't have any yellow sections. And then blue with an odd number, I see 2 of those. So 2 out of 8, which is 1/4. So just how many outcomes are possible, and then how many match whatever that little situation you've been given to find the probability of. A simulation is something that would give you a particular number of outcomes that you would expect. It's used to find probability. So if I was wanting to have a simulation that would give me 2 equally likely outcomes, I could do the simulation of tossing a coin because I know that gives me heads and tails. If I wanted a simulation of 6 equally likely outcomes, I could roll a number cube because I know there's 6 equally likely sides on it. I could have an 8-sided spinner for 8 equally likely outcomes. And then remember, I can use the simulation to make a prediction about which is closest between the theoretical probability and the actual experimental probability, the actual data. So if I was going to simulate 99 days of spinning the spinner, notice there's 3 equal sections. What would I expect for it to land on? I would expect 33 setting the table, 33 clear the table, 33 wash the dishes. And then I just have to compare that to the actual experimental probability that I got in this table here. Which of those is the closest to what I would expect? Blue, 32 is the closest to 33. The other 2 are further away. So I would say that blue, which is clearing the table, is the chore given by the simulation closest to the number predicted by the theoretical probability. All right, now let's move on to compound events very quickly. We know that in a compound event, the action is going to be a multi-step action. So not just flipping a coin or spinning a spinner once, we're going to do something multiple times. Okay. Compound event, it's associated with a multi-step action. We're going to have the list of what we're expecting to get here. Select spin red and then spin green. And we would find the probabilities of those. Which of these would match the spinner? Spin the spinner 4 times. It would be the second one and the third one because we see 4 outcomes. This first one only has 3 outcomes. That wouldn't match this event. All right, now let's review the difference between independent and dependent events. Independent events are when you do an action, and then the second time you do the action, you have the same number of options. So like if I drew a tile out of this little selection here, I would replace it, meaning I would put it back in. So I would still have 11 possible outcomes the second time I drew. That is independent. So the number of possible outcomes is not changing from one time to the next. Whereas dependent events, if I drew a tile out of my little selection, I would not put it back in. So now instead of having 11 choices, the second time I draw, I only have 10 because I didn't put the tile I drew the first time back in the bag. Okay, so that's the difference between independent and dependent events. Remember, there are 3 different ways to represent the sample space that we talked about. We could make an organized list. We could put a table together where we combine like the row and the column labels, or we could make a tree diagram, and that just helps us see our sample space. So I'll just review really quickly with you how to do this. We could do peach, strawberry, and banana. So peach, strawberry, peach, banana, and then peach, peach, strawberry, peach, strawberry, banana, strawberry, strawberry, and then banana, peach, banana, strawberry, banana, banana. So we get 9 possible combinations. If they told us that they had to be different flavors, I would have to eliminate these bottom 3. Because those have the same flavors. Okay, you can do the same thing by making a table or by making a tree chart, a tree diagram. We practiced these when we did this the first time. It hasn't been that long ago. Remember, for the tree diagram, you would just give all the possible options. There's 2 seats. So for seat 1, I could have a 6th grader, a 7th grader, or an 8th grader. And then in seat 2, I could have a 6th grader paired with a 6th, 7th, or 8th grader, a 7th grader paired with a 6th, 7th, or 8th grader, or an 8th grader paired with a 6th, 7th, or 8th grader. So that gives me 1, 2, 3, 4, 5, 6, 7, 8, 9 combinations. And that's using a tree diagram. All right, next, remember the counting principle or the fundamental counting principle. You just figure out how many choices you have for each category, and then you just multiply them together, and that gives you the total number of combinations. So here in the chili, we have 1, 2, 3, 4, 5 choices for the temperature of the chili. And then we can either choose with or without cheese. That's 2 choices. 5 times 2, we have 10 different combinations of chili. Okay, so that's how we use the counting principle. Last, finding the probability of getting exactly 2 boys. We would just have to count up. We have 1, 2, 3, 4, 5, 6, 7, 8 different combinations. How many of those give you exactly 2 boys? I see 1 combination here, and then a 2nd combination here, and then a 3rd combination here. I think that's all of them. So it would be 3 out of 8 would be the probability there. Last thing is writing the probability. We just talked about this. But writing it like as a fraction, let's do this one, and I'm almost out of time, but here we go. The probability of at least 1 apple. See, they've given us this table here that has all the possible combinations of sample space. I just looked how many have at least 1 apple. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of how many total combinations? 25. Okay, so you use either the list, the tree diagram, or the table to get your sample space, and then you just count how many out of the sample space is going to give you whatever the probability you're finding. Okay, this has been a real quick, real brief review of probability. This was one of the last units we did, so it should be hopefully pretty fresh in your memory. If you have any questions, please ask me, and if you need help with the digits review also, I'm happy to help you.